Okay, so we started with joint PMFs, and then based on that, we talked about joint CDFs. And these properties we have derived for general CDFs, in fact, general joint CDFs. So what I mean by that is the properties listed here are valid for joint CDFs for discrete random vectors, but also for continuous random vectors or mixed type random vectors or with random vectors with some components are discrete and some of them are continuous or mixed type. So these properties are quite general. Um, so for any random vector, the joint CDF will satisfy all of these properties. For discrete or continuous or a mixture, doesn't really matter. These are universal properties. But in a more general sense, of course, if you recall, we can also represent a PMF using impulses. We can represent it as as a PDF. Therefore, in a broader sense, we will now describe how to work with joint PDFs. And what we talk about here will be, of course, valid for continuous random vectors, but they will also be valid for mixed type and discrete random vectors while using impulses to represent probability masses. Okay, so to define joint PDFs, we first of all, again, as we did with continuous distributions, we discretize the space into small grids. In the real line, well, what we did was discretize it using into uh, small slots. But here we have a grid in the 2 dimension. And in 3 dimensions, that would be infinitesimal cubes and so on. So what we are doing is we are actually concentrating probabilities in each of these small infinitesimal areas, denoted A sub jk for the event A, so that we are essentially approximating a continuous distribution with a discrete one. But then we will take the limit and these squares will diminish to points, and at the limit, we will have a continuous distribution. So the probability of event A can be written as the probability of the union of all of these small squares. Okay. However you enumerate them, if you add them all up, you get the probability of A because you see these are all disjoint. So this is the summation across both dimensions of the probability of each of these small squares. And we can actually write the probability of each infinitesimal square using this. This is, you see here, is the joint PDF, and delta x1, delta x2 is the steps here. So delta x1 is this distance, and delta x2 is this distance. Of course, when you multiply them, you get the infinitesimal area. And this is similar to what we have done in the one-dimensional random variable case. If you remember, for a continuous distribution, we had probability x less than random variable x less than or equal to x plus h. When h is sufficiently small, this was at the limit would be equal to the PDF multiplied by h. Okay, and so that is what we are doing here. We are discretizing the continuous distribution, and we represent each of these probabilities with this joint PDF multiplied by the infinitesimal area. But when you take the limits as delta x1 and delta x2 goes to 0, again, based to this Riemann sum, you get a double integral over this area that defines the event A. You get a double integral of this joint PDF dx d2, dx1 dx2. So essentially, you see, this area can be, well, something like this. Let's say this is x1 and x2. In this case, you see this will be the event x1, random variable x1 less than or equal to parameter x1, and random variable x2 less than or equal to parameter x2, which gives me the joint CDF of x1 and x2. So the area here is this region, and therefore the integral, this double integral will be minus infinity to x1 minus infinity to x2, the joint PDF integrated. Of course, I have used different parameters here so that I can use x1 and x2 in the integration limits. Therefore, when you have this relationship, I can write the joint joint PDF as the 2-time derivative of the joint CDF with respect to x1 and then x2. Okay, so in general, the distributions we deal with will be indifferent to the order of the differentiation here. So we are excluding some pathological cases. Therefore, the order here will not be important in general, at least for our purposes in this course. And finally, we can write this probability that we have talked about here using this integral from A1 to B1 and from A2 to B2, the integral of the joint PDF. So this is how you use the joint PDF to obtain probabilities. And this is the relation between the joint PDF and the joint CDF.